Hi guys, welcome to our channel of Sciences and Mathematics. Today we are going to look at some of the characteristics of the cross and dot product of vectors. And this is going to assist us to define some of the theorem that we are going to encounter maybe when we are trying to do application of these specific vectors. Now we're going to mention one or two theorem, and maybe the third one we're going to look at it into details when we will be having our discussion on the next video. So without further ado, thank you and welcome. So as I've said, today we're going to look at some of the characteristics of the cross and dot product of vectors. And this is going to assist us to define some of the, or maybe understand some of the theorem that we are going to encounter, or the theory that we are going to encounter, and some of the application of these specific vectors. Now we have talked about the concept of cross and dot product of vectors. And of course we have just put a dot and cross product. Now normally we not have to just put an encompassment of both the dot and the cross product, but in trying to put up this specific topic, I'm trying to do a comparison, or maybe some of the concept that is going to exploit the characteristics of both the dot and the cross vectors. And now we're going to do that one using one of the examples that I'm going to write on the board. So that one will be in the form of a question where we'll be required to solve a problem, and then we will just get the behavior or characteristic from there, which will assist us, of course, in trying to define this theorem that I've talked about. So for that case, we are going to consider two vectors. So we consider the two vectors u, which is given as 1, 2, -2. So these are the specific values for this vector in three-dimensional space. And then we're going to have so this is u, and we're going to have v given as 3, 0, 1, just like that. So these are two vectors and two-dimensional space for u and v respectively. So therefore, if we're going to find the cross product, this is u cross v for these two vectors, we can just use the concept of course, the concept of determinants for us to find the u cross v of this specific vector. So it's going to be 1, 2, 2, and then 3, 0, 1. So we just write it in form of a matrix, and then we are going to find this for the components of I, j, and k. So perhaps I can just expand it and try to write it on this other side so that we can be able to just do it. So this is 1, 2, -2, and then this is 3, 0, 1. So for I, this is I, j, and k components. For us to find the determinant of the cross product of this specific matrix, we are going to just to take the first column, and we know it, so it's going to be 2 times 1, that is 2 minus 0. So the first one for I component is going to be 2i, and then minus, we take the second one, this is 1. So this is going to be for j. So it is 1 minus 6, and then plus the last one, this one. So this is 0 minus 6. This is for the k component. So therefore, this is going to give us, just expanded this one for the sake of the negative sign. So this is going to give us 2i minus, this is a positive, 7j plus, so this is minus because of the -6, so minus 6. Okay, so therefore this is going to give us that specific vector. So the components of this vector, we can be able to represent it. The resulting vector from this is going to be represented as 2, negative 7, 6 for the I, j, and k, or x, y, and z direction. Now, suppose we have another challenge whereby we are asked to consider the product between a dot. This is u dot, the cross of u, v, and we are requested to find the product for this. So I'd like us to just have this one in mind somewhere. This is the product between uv, the cross uv. So therefore I'm going to do away with all this so that we can be able to work on this other second one. So in that case, I just write it somewhere that the product uv, that's the cross of uv, is giving us 2, negative 7. This is a negative 6, negative 6, just like that. So therefore, we're going to have a cross for u. So this is just going to, our initial vectors were u for 1, 2, negative 2, and then v, 3, 0, 1. These are the ones that we have used in order to do a cross for u and v. So therefore, I'm also going to use this particular vector u for us to find the product for u dot v, u cross v, and try to see what our product is going to be. So I'm going to take this component for dot product. We said that for I dot I is equals j dot j is equals k dot k, which is equals 1. So we're going to see that one maybe when we are trying to discuss another aspect, but for that case, this is one of the concepts that we have to take note of. So therefore, in this case, we're just going to multiply this component by taking this vector times this one, and it's going to give us 1, 2, negative 2, and then a dot product for 2, negative 7, negative 6. So bear in mind that this is u dot u v. So we are trying to find out what is the product for that. And this is when we multiply the respective components. So we'll find the sum of the respective components, the product of the respective component. This is 2 times 2, 2 plus, so the sum of that. 2 times negative 7, it's minus 14. And then this is minus 2, so plus minus 2 times 6, this is minus 12. So in this case, because this was actually negative 6, which I had just written here, this is going to be plus 12. So this is going to give us the sum for, this is 2 plus 12, 14. So it's going to give us a 0. So therefore, there's also another second example that we are going to see. So this one, the product of this one gives us a 0. So let's look at another example. So this one we have done, it is u dot the cross of these two vectors. Suppose we take v as another component and then have a cross with this, so it's sorry for that, v dot u cross v. Let's try to find out what it's going to give us. So for v, it is 3, 0, and then 1 dot, still uv. For this one, it's going to give us 2, negative 7, negative 6. So let's try to find out what that one is going to give us. This is 6 plus 0 minus 6. So this one also is going to give us 0. So what I want us to look at is the characteristics way in which if we take a component of these two cross of vectors out and then we do a dot product with it, it's going to give us 0 for u and v respectively. So whenever vectors or the product of these two kinds of vectors are going to give us those specific values, then we can say that the two vectors or the vector just a minute. Then we're going to form some of the conclusions from this specific behavior. So I hope that we have seen how we have achieved the product for that from this specific calculation, and for the second one by trying to take out the specific components of this cross product and trying to multiply it times trying to do a dot product of the one of the zero. So I'm going to come up with a specific conclusion. Therefore, I'm going to have a statement here which will assist us to know the characteristics of those specific vectors that we have dealt with. So this is it. If u and v are vectors in a three-dimensional space, then A u dot u cross v is equals 0. So that is the one that we have illustrated from the example. Then it implies that u cross v is orthogonal to u. So therefore, when the cross between the product between u and the cross uv gives us a 0, then implies that this particular set of expression is orthogonal to u. And then b, we're also going to have a second statement from that. V dot u v 0, whenever it is equals to 0, then u cross v is orthogonal to vector v. So this basically implies that the concept of orthogonal implies that this particular vector is perpendicular to this one. So in this case, we're going to see that this is going to assist us in trying to define some of the rules that we're going to encounter maybe in applications in physics and mathematics. And that is going to, of course, assist us in trying to solve some of the problems or see some of the behavior of some quantities and maybe in magnetic fields, magnetic or electric fields, which are going to apply this behavior and are using the right hand system, which we are going to discuss basically in another video. So I'm just going to leave that one there. So in this case, we have just derived two statements from the calculations that we have done using the concept of these in order to define orthogonal vectors. So these orthogonal vectors basically refers to the concept in which vectors are perpendicular. So if I can do an illustration, maybe this is if this is vector u and v in that specific direction from this point, then it implies that this vector resulting vector is going to be perpendicular to either of these two vectors when we're going to do a cross of those specific areas. And there's one that I'm going to mention, of course, but we'll just deal with it in another area. Now this is going to find an application in what we call the Lagrange's identity, as of course it's going to be dealt with independently, as I've said. So in this case, this is opening up just a discussion for those specific topics that I've talked about in mathematics and physics, which is basically going to entail the use of the right hand system that we're going to see being applied in electricity, magnetism, etc. So for that case, I wanted us to just note the characteristic of these specific vectors so that whenever we come across them and I mention the term orthogonal, we're not just being maybe left to wonder what it specifically entails. So in that case, I hope that this concept is clear and we're going to apply it appropriately once we come across it. So that is it for today, guys. Thank you. Bye. God bless you.